So in the last video, we did some work to determine a Maclaurin series for sine of x. The Maclaurin series for sine of x ended up being the series that we have right here. So we built that series from scratch. We had to take some derivatives. We used the definition of a Taylor series in order to produce this series. We determined the interval of convergence for this series was negative infinity to infinity. And then we also looked at some Taylor polynomials produced from this series graphed along with sine of x and saw that it was a pretty close relationship without having to use awfully many terms. Now what we would like is we would like a series representation for cosine of x. So you would hopefully agree with this argument. If I take the derivative with respect to x of sine of x, what I end up with is I end up with cosine of x. So when you looked at power series, you probably developed power series that were related to geometric series, and then took derivatives and antiderivatives of those series to develop power series that converged to the derivatives and antiderivatives of the functions that the original power series converged to. And we can actually exploit that relationship here. If I take the derivative with respect to x of sine of x and I get cosine of x, I should be able to take the derivative with respect to x of this side of the equation to produce cosine of x. And what I'm going to have to do on the other side is I'm going to have to apply the same thing. If this is an equation, if this series converges to sine of x, which we haven't proven in any of these videos, but that theoretical aspect of this we're kind of putting on the back burner for the time being. But if this sine of x series is, if this function sine of x is equal to this series on the entire stretch of the x-axis, then taking the derivative of both sides of the equation is going to give us a new equation that has to be true on the same interval. So let's go ahead and think about what happens when we take the derivative of this. So the summation is going to copy right in. This coefficient is going to copy right in. There's no x within that fraction that's out in front of x to the 2n plus 1. So that is going to copy in, right? We can always copy constants into our derivatives when we're taking them. And then I'm just going to apply the power rule. So I'm going to multiply by 2n plus 1. And then I'm going to have to subtract 1 from that exponent. Well, when I subtract 1 from 2n plus 1, the 1 goes away. It just becomes x to the 2n. So from there, what we can do is clean this up a little bit. So cosine of x is going to be equal to the sum from 0 to infinity, negative 1 to the n. Here's what I notice. 2n plus 1 in the numerator right here from taking that derivative. 2n plus 1 factorial down here. I've got a 2n plus 1 here that's going to be able to cancel with the 2n plus 1 in that denominator. Now, you have to be careful when you're canceling factorials because a factorial is a big chain of multiplication. Hopefully you can convince yourself that when we cancel that one factor from that factorial, what we're going to be left with is we're going to be left with just 2n in that denominator, and then the x to the 2n is just going to copy right in. Now, again, my notation is, I guess, a little sloppy because I haven't proven that this series converges to sine of x. I haven't dealt with Taylor's remainder at all. If you use Taylor's remainder, you'll be able to prove that this does converge to sine of x on the entire stretch of the x-axis. So assuming that we have done that, this work is valid. We now have a series representation for cosine of x. We'd be able to use Taylor's theorem. We'd be able to use Taylor's remainder to prove that this series does converge to cosine of x. We could use the ratio test again to prove that the relationship holds on the entire stretch of the x-axis. So what you have here is you have these series representations for sine of x and cosine of x, which definitely resemble each other. The one for sine of x has the exact same form as the one for cosine of x does. The only difference is we're looking at something that's always odd in this factorial and within this exponent, and we're looking at something that's always even within this factorial and within that exponent. So here's the nice way to kind of come to memorize these series. If you think about the graph of sine of x, the graph of sine of x is going to go through the origin. It's going to look something like this. The graph of cosine of x looks similar to that, but it doesn't start in the same spot. Cosine of x is going to start up on the y-axis at 1 and then go through its cycle. The graph of cosine of x and the graph of sine of x have opposite types of symmetry. Sorry about that. That's why you never do your math in pen. Made a mistake, had to scrap it, and start again. So what I was trying to say is sine of x and cosine of x have different types of symmetries. Sine of x has what we call odd symmetry. Cosine of x has what we call even symmetry. So this is something that you've maybe studied in pre-calculus. Even if you haven't, I'll try to explain it to you here. And this is a nice way to remember the series representations for sine of x, which is this, the sum from 0 to infinity of -1 to the n divided by 2n plus 1 factorial times x to the 2n plus 1. You'll notice that odd factorial, odd power. For cosine of x, we have the opposite happening. 2n factorial in the denominator, and then 2n in the power, even factorial, even power. So if you already know what even and odd symmetry are, then hopefully you recognize why this is a useful thing to talk about and use to remember the series representations. The Maclaurin series representations for sine of x and for cosine of x. If you haven't been exposed to odd and even symmetry before, try to explain it to you here. So a function with odd symmetry is symmetric about the origin. That's a graph of y equals x. If I called this a polynomial, you would say the degree of that polynomial is 1. A graph with even symmetry has symmetry about the y-axis or across the y-axis. That's a graph of y equals x squared. So if you just kind of remember that an odd function is an odd degree polynomial like y to the x, symmetric about the origin. An even function is an even degree polynomial like y equals x squared, symmetric across the y-axis. That can hopefully, if you know what the graphs of sine and cosine look like, symmetric about the origin, symmetric if I flip across the y-axis, that can hopefully allow you to avoid mixing up the Maclaurin series for sine of x and cosine of x. So in the last video, when we developed the series for sine of x, I said in AP Calculus, you're going to want to make sure you memorize this. You're going to want to make sure you memorize this as well. There are 3 series in AP Calculus that you'd be in really bad shape if you didn't have them memorized going into the AP exam, and that would be the 2 that are on this screen here, and then we'll add one more to the bottom here, and that is the series for e to the x. So the series for e to the x is from 0 to infinity, 1 over k factorial times x to the k power. So in AP Calculus, you want to have this, and this memorized. Might you need other series on the AP exam? Yeah, potential's there. The good news is, usually when we do, they provide those series to us and then ask us to do something with them. But they don't typically provide the Maclaurin series for these 3 major functions, sine, cosine, and e to the x.